Okay, so hello everyone. I am Dr. Mastan. I am from IIT BHU Computer Science Department. What I am going to discuss today is deep internal learning for image restoration. So when I say restoration, we are not thinking in terms of what we have discussed so far. What I am saying is you have an image which is corrupted, and maybe that image is corrupted or that image is taken of an object which was corrupted. Right, so you have that image, and what you want to perform some kind of image enhancement or image restoration. Means you want to, let's say if the image is taken of an object which was corrupted, you want to synthesize the missing objects. Or if the image is corrupted, how do we restore the pixels? Because when you think of, at the end of the day, image is nothing but you have some matrix, and this has some values. That values is between 0 to 255. That is the digital image, right? So what we are discussing in this presentation is how do we do the image restoration. And I work in computer vision, so the computer vision is part of AI, artificial intelligence. So I'll be discussing about some of the basic way through which I have done the image restoration. That is mainly I started in my PhD duration, and then I have also, so I am a professor, so I have also a couple of projects which are there, and also some of the students regarding this. One thing I want to mention before I start, this deep internal learning, this is one of the recent research area. It's not, so when I was in 2017, when I was searching for or hunting for research problems, this was not formalized as a research area. But the deep internal learning, because of the need, the kind of restoration techniques we require nowadays, this developed slowly into a research area. It was only started from the Oxford University, then some of the Israeli group and some of the Indian groups started proposing methods for the image restoration task. So this is the deep internal learning for image restoration. Okay. So basically, when I think, so I'll try to simplify a thing as much as possible. But if I'm not clear, please interrupt and you can ask. So what I'm saying is how the computer will restore any image, how AI or how your computer vision techniques will do that. So mainly what is happening there is they already have many paired samples of the corrupted and the restored version. Many paired samples they have. So for suppose if it is an image denoising problem where you want to remove the noise, so they will have they will take some specific good quality image, add noise. Now you have the image pair for the corrupted and the restored version. Similarly, if it is a image super resolution problem where you have image which is very much of low resolution, you want to improve its visual quality. So what they do, they will take some image, do it low resolution, some operator, and then you have a pair. Or maybe image inpainting problem where you want to fill missing regions in an image. So in that case, you take some image and then you corrupt some of the pixels. So how the classical way or the supervised way these things are happening is like they will have many paired samples, xi and yi. Xi is your corrupted image and yi is your so xi is your restored or good quality image and yi is your corrupted image, and they will feed that into a model. What do I mean by a model? Basically think of a function. It's actually a function of functions, or I would say the functional composition, or but what they do, basically they have this data, they feed this data and provide this data to a model, and then model will try to learn the mapping from the corrupted to the restored. This is what model will do. You will supply it some existing examples, and then the model will learn this model. How do we understand this model? The model, if I say the model is f, that theta is the parameters of the model. Means at the end this function or the model has some parameters, and then you that parameters will decide how it will do a mapping from the corrupted to the restored version of an image. So after feeding through many samples and training a model to learn this mapping from the corrupted to the restored, then you have a best set of parameters for your function or your model, that is f theta star. And then what you do, For any corrupted image, you supply that into the model, and then model will map it to the restored version. This is how classically supervised learning paradigm used to handle these problems. This is, I am not mentioning about the handcrafted filter. If you remember, if you have used Adobe Photoshop, or if you have used any of these software packages, what they are doing, they are actually using some kind of handcrafted filter. What do I mean by handcrafted filter? Think of a simple matrix. Image is nothing but a matrix. It is multiplying that with matrix, and then accordingly what is the output? Two matrices are multiplied, you have another matrix, that is your image. And that handcrafted filter is well designed in the software. What I am discussing over here is, we don't know what type of or what degree of the corruption is there in an image. So our classical softwares which we do or which we use for the restoration, their filters will not work. In that case, we have to actually learn a specific model F which will do the restoration for us. So this is how the classical thing used to happen. And there are some of the limitations of this classical strategy. Is like, one of the first thing is you need the annotated data set. You need the pairing of the corrupted and the restored version. Many samples you require. And also, I would say one of the challenging tasks also is training this model. Because when you are training your model for lakhs and lakhs of image, you really require a lot of computation. So if I want to give you just how big these computations are, suppose if you have, so whenever you take an image from your mobile, right, it will be higher resolution than 1024 cross 1024. Right, and I say this is an RGB image, means you will have 3 channels. So it will, and each value in that pixel will be from 0 to 255. You have a image space which is something like 256 to the power of 1024 cross 1024 cross 3. That is the huge dimensional space in which all of these points are nothing but the images. So exploring that space is not at all feasible. That's more than the particle in the universe, right? So what we do some intelligent trick through which we only, because the natural images will occupy only the tiny fraction of that image space. So we will do some simple tricks through which we learn this mapping from the corrupted to the restored version. So the classical supervised learning strategies are when you are to train model for lakhs and lakhs of images. That is one of the difficult thing, to also get the resources. And when I was in my PhD, this was the first question was asked by my supervisor. Why do you want to utilize so many resources? The intelligent person will say that I will use minimum number of resources and I will do a very good quality restoration. Try something of that sort. And I was lucky because that time Deep Image Prior, one of the famous work came from Oxford University, and they were doing it without these paired samples. What is happening here is, what they trained is the image specific functions or image specific networks. In that case, you only have an image, you supply it in your model or your function, and then you will get the restored output, and you iteratively refine what is the output of the model such that it aligns well with the good quality image. That was one of the first work, and over the same time, like some of the new works have also came, and I was lucky that I figured out that thing, and then I thought maybe I will pursue this. Why? Because and this is, at that time it used to be called as training with no prior example methods. But then it developed as a research area and it started as a name as deep internal learning. So what is the motivation to work in these kind of areas is like what kind of problems you can solve. You cannot solve the classification problem in this setup. Because if you want to, let's say, have so many images, maybe you have images of dogs and cats, right? If you want to learn a computer model which will give an image and it will tell whether it is an image of a dog or whether it is an image of a cat, it cannot do that with only 1 or 2 instances. It really requires a lot of training samples. So those things we cannot do through deep internal learning, but the restoration part or the image enhancement part we can do through the deep internal learning. And that was one of the primary motivation. And what tool we will use? So mainly when you think of any specific images, you also have many information in that image. So much information is there. And that information need to be put up into a mathematical framework such that when we utilize or work as part of that mathematical framework, you will be able to restore that image. That is the ideology. So, and mainly in this case, you do not have the dependencies on that having a large training samples. So for example, if I relate it to the manuscript restoration problem, in that case, you have only the corrupted images or images of the corrupted manuscripts. You don't have the ground truth, right? When I say, let's say this manuscript is 1,000 years old, I only have the corrupted version. I don't have the restored version. The ground truth I don't have. So this problem naturally aligns, the deep internal learning and naturally aligns with restoration in the context of old historical manuscript. So that is one way through which we can see that deep internal learning is a very good motivator to do the restoration of the old manuscript images. And one more important detail about the deep internal learning approaches is they are not computationally heavy. Because what we are actually working on, some kind of unsupervised or the self-supervised. Why I say it unsupervised? Because you are not training a model or you are not training a function with respect to a specific mapping from the corrupted to the restored. You are just giving a corrupted image. And then the model will automatically understand how do I restore this part. Right? So this is actually the part of unsupervised learning strategies, and this is not very computationally heavy comparative to the supervised learning. So that was one of the important goals also completed, that it should not be computationally heavy and it should also work align with the kind of images which we have. So these are the motivation. So this is one example manuscript I have taken from the Wikipedia. This is, you can see, one of the old manuscript. And now what I want to introduce you to the different type of corruptions that can happen, right? So when we have a specific old manuscript image, right, you can see that image and it can be like some kind of noise can be there, some kind of inks spread or some kind of stain or fading. Those kind of problems can be there when you think of the images, right, of the old manuscript, and you do not have the ground truth available in this particular scenario. So when you have, so what kind of corruptions can be there? So suppose you have, this is your ground truth. This is actually I curated for this particular presentation. So you have this ground truth, and when I add noise, your noise is something like this. The noisy manuscript is like this. Now what we want to restore this to match with this quality. Or suppose you have the color distortion. So the manuscript image will be looking like this. Or maybe you have some of the region which is missing. So this can also be there in the manuscripts. Or it may also happen that your image got corrupted and 50% of the pixels are removed. In that case, this kind of inputs can be there. So in all of these different scenarios, what this deep internal learning will do, it will help us to achieve this kind of restored output. This is, I'll be discussing. So this is mainly the ideology for in the context of old manuscript restoration. So now what is deep internal learning? Deep internal learning is nothing but a learning paradigm through which we train deep neural network. So if you have not heard of what is a deep neural network, you think of that is nothing but a function. And that function has some parameters, right? And then what you do, that function is going to map something, an input to an output. And your input in this case is a corrupted image, and your output is, in this case, is the restored image. So all of those corrupted images are the input, and the output is the restored image in the case of deep internal learning. Okay. And why this work? Because this is the unsupervised learning domain. Why this work? Because there are so many information which is there in the image itself, the corrupted image itself, that help to restore that image. So those are formulated in the form of mathematical framework, and those are called self-similarity prior or the implicit prior from the network or the generative priors. So these are the different mathematical terms which are put up to show the mathematical framework through which we can model the properties of the natural images. So when I say the self-similarity, so suppose you have an image like this and you can see many patches are similar. right? If I take any particular image and I think of maybe, so if this is a, let's say 100 cross 100 image, many 5 cross 5 patches will be similar to each other. I can utilize that 5 cross 5 small patches to restore the corrupted part. So that is actually mathematically formulated in the form of self-similarity prior. Similarly, something is very good about these functions or these deep neural networks. Mainly, they are implicitly observed or experimentally observed that they are very well aligned with the restoration related tasks. They have not, so it's not mathematically proved, there is no theorem which is given so far, but it is observed. It is observed that it has a behavior that when you give a corrupted image, the parameters will align such that the output image will be a restored image. The mathematical explanation people give in the form of priors. What kind of, so prior means what is actually there in that particular image. So people give, but nobody has so far give a mathematical proof or any theorem that this work. But I can still say this is a good thing to pursue because the pioneer who are there in this field, they have got the Turing Award and the Nobel Prize Award both. So this is actually supported by the Geoffrey Hinton, who is the father of deep learning, and he has got, because very few people are able to get both Turing and Nobel. So he has got both the awards. So I can say that there is actually a very good value when you work on the research areas of AI and computer vision. Okay. So the network structure which we are going to describe, that can also provide some kind of prior for the restoration task. Okay, and then this is a little bit classification. So what we have is the broader categorization of deep learning, and then you have two types of method. One is the supervised and another is unsupervised. The supervised method, you can at a very basic level say they are training example based methods. And what we are discussing is the training with no prior example methods. Because this is what we have. We don't have ground truth for the corrupted images, the images of the corrupted manuscript. So we don't have the ground truth. So we are actually in the regime of training with no prior examples, and there are further categorization of that. One categorization is when you are not using any feature extractor, means you are using that function which maps from the restore to the from the corrupted to the restored. The parameters are randomly initialized, some garbage value. But then through the learning mechanism, that parameter will adjust in the training phase, and then you will have the restored output. So when you are not utilizing any feature extractor, that is the first category of method. DIP was one of the first work. This is our method and other methods as well. Similarly, then the second category is using a feature extractor. What do I mean by feature extractor? Suppose you have a model which is trained on classification task. Because many of the researchers in the field, only academics will do that. Like what they do, they collect lot of data, millions and millions of images, annotate them through their projects, and then train a specific model. Model means that function, and give the data set and the model for free for everyone to use. Means you are doing, let's say, research for 3 to 4 years, and you are giving everything for free, and that only academics will do, not the business strategies will do it for you. So many of the people from Stanford and other great places, they have actually given us a very good model which are very good feature extractor from images. Means when you are supplying any image, it will identify the features very well, and then you can use those feature extractor to perform the restoration. So both ways, your mapping or that function can be think in terms of the starting from the scratch, or you can also use some kind of feature extractor, and these are our works for the case when you are using a feature extractor. Okay. So now mainly I have described the two branches. One is like when you are thinking of learning from the scratch, and second when you are using a pre-trained model to perform the restoration task, and these are some of our works. Which are published in top journals and conferences. Okay, so now let me describe the different type of frameworks which are there in the deep internal learning, and this list is growing on because this is a growing research area. One of the first survey paper for deep internal learning came 2024 only. So these are some of the categories: the reconstruction based restoration, decomposition, style transfer, and generative modeling. So but what I want you to understand is this. So think of, so there are different abstraction when you are performing any specific application. What are that abstraction? So at the foundational level, you will have some network or some function which is sitting. That function or that network will have some specific structure or some specific design which you are going to train. So that is nothing but your tool part when you are thinking of at a lowest level of abstraction. But then what you do, you have that function or that network, utilize what is your objective, what you want to perform, and then you combine both of them, objective or in the form of loss function and your tool, which is nothing but your network, and then you propose these different frameworks. These frameworks, let's say image reconstruction means you have an image, you feed that, so your function is mapping an input or an output of the same size. So you are just doing the reconstruction part. So that is nothing but your image reconstruction framework that is mainly suitable for the image denoising related application. Then you have image decomposition framework where you decompose an image. Suppose you decompose means, let's say if you want to think of doing the segmentation of the characters which are there in the manuscript. So something is there in the foreground, something is there in the background. So that is nothing but the image decomposition part. Or maybe you have a natural scene where the haze particles are there. So you want to remove the haze from the scene. So that is again an image decomposition problem. So this is the second strategy, the image decomposition. Third strategy is the style transfer. Means suppose you have an image in which the style features are not very well, not good. The manuscript is very faded or the colors are not coming out, the texture is not coming out. So those frameworks are formulated in the form of style transfer works. And lastly, what you have is the single image Gyan. So mainly this is for the synthesis part. Means you give an image and it will, you give so many samples to the your model and it will start learning how to synthesize. So maybe you have heard of deep fakes, like AI is creating faces of humans which are not even, doesn't even exist. Right? So those are nothing but your generative model, and Gyan is one of the generative model. And why we need that generative model in the case of restoration? Because sometimes it may happen that in your manuscript image, it is so corrupted that you need to synthesize some of the part. So over there you will require the generative models to be specific. Okay. So now what I'll do, I'll describe these in the form of some mathematical detail. So just see the intuition of this equation. What is happening here is, this is your model F. You can feed that model with some noise, or you can feed with some different version of your manuscript image. Both are fine. In theory, people have proved that both way, if you are initializing the network, it will restore. So that Z is your input, theta is the parameter which you want to figure out. And that theta, because when you are applying this Adobe Photoshop or all of the software, they had the theta means the parameter or the well-defined matrix which we are going to multiply. But the kind of restoration we want to do, for that, that parameters is not known, or that kernel is not known. So you train a specific network to identify the best set of parameters theta. And this F is nothing but giving an input, it will give you the restored output. And what do? You take that image, do this H is denoting a degradation function. Means what you did, you supplied either a noise or some image to the network. Whatever is the output, you degrade that output and match that output with the manuscript image. It is something like, I have some restored image, I degrade and then match. Match means pixel by pixel computing the difference. It's a pixel to pixel loss. So pixel by pixel you compute this difference, right? And why this is a minimization problem? Because you want to identify the best set of parameters for which, when there is no difference in the output of the network, when degraded it matches with the given image. So intuitively this framework works. And this is the, so now depending upon what kind of restoration task you do, accordingly you can set this H. Whether you want to do the in-painting task, whether you want to do the super resolution task, whether you want to do the denoising task, accordingly you can change this degradation function. So it's saying you have the output of the network, do the degradation part, and then match it with the manuscript image, and then it will match, and accordingly the network will have the good set of parameter to give the restored output. So this is mainly the foundational idea which was proposed in 2018. Okay. So now through this we can actually perform all of these different restoration tasks. Maybe I'll first describe the image denoising task. So in the case of image denoising, your H is nothing. H is an identity function. So what do you do in case of denoising? You take a some noise, some specific image of the same size of your corrupted manuscript image, which is Y. You feed it into your model and then do a pixel to pixel difference, and accordingly optimize the parameters theta. The problem with this kind of approaches is like it will start, so obviously initially the network is not trained, so it does not have the best set of parameters. So in that case, initially the outcomes of the network will not have a very good quality. But slowly the quality will match, right, with your ground truth. We don't have the ground truth, obviously, but we can actually measure the quality of an image in the non-reference setting as well. So you have your output up to your best level, and then it will overlearn the noise as well. So then quality will degrade. So in that case, what you have to do the early stopping. That is one of the strategy. Means the network will first learn the image features, and before it start to learn the noise, because it's a pixel to pixel difference, according to which we are updating the parameters, right? So before it start to learn noise, you just stop there, and then you have a good quality restoration. So this is the image denoising application. We have the MDS and DCIL framework, which we have proposed on top of this, and mainly in these works we have described what kind of network architecture is required for the restoration, because for each of the different restoration tasks, right, you have a different structure of the network. So in that study, we only figured out how the restoration quality is getting influenced by the structure of the network. Okay. Next, suppose you have the restoration of mainly the in-painting task. Means you want to fill in the missing pixels. So for example, you have a manuscript image in which you have some of the regions are missing, or maybe something like 50% of the pixels are missing. It works even at the 90% pixels. I have not put up that slide because when I see 90% pixels are removed, I cannot see anything. But the network is able to see. So it works even at the 90% removal of the, so the means arbitrary removal. Region in-painting is much difficult. This is what we are discussing about, the arbitrary removal of the pixels. Okay, so what is the scenario for the image in-painting task? So for the image in-painting task, what you do? Basically, you have the output of the network, which is this. And you have your corrupted manuscript image. You match them. This is actually Hadamard product. Hadamard product with M. What is this M? It's nothing but a mask. It will be 1 for all the places where you have the image features, and it will be 0 for the places where the pixels are missing or the image features are missing. So you have this mask of 1s and 0s, and what you want, whatever is the output of the network, you want to match that with the corrupted image only at the feature space, not at the where the pixels are missing. And this is what this Hadamard product is doing. It's the element wise multiplication. So means what is happening is, this is the output restored image, and this is your corrupted image, and wherever the image features are there, over there you are doing the pixel differences to update the parameters of the network. You are not updating with respect to the missing region. The ideology is, when you are updating the parameters according to the image features, when you are updating the parameters for the image in-painting task for these places, this will also automatically fill. And it does experimentally. So this is your mainly the image in-painting framework. Next, what we have is Yeah, so we had worked on MDS, and these are our frameworks which we have used for the image inputting task. And the good thing about, you are able to perform the restoration without the ground truth and only the internal features which are present in the image. Okay. Next is the image decomposition task. So you can see this image decomposition problem with these kind of motivating examples. So when you see, these are the three different examples. One is the image segmentation, another one is the image dehazing, then you have the transparency separation. These are the different examples. So what is happening here in the case of image segmentation? You can think you have some kind of mask. That mask is differentiating between the foreground and the background. And in this particular image, your mask is differentiating between this zebra and the grass, right? So over here, this mask is basically highlighting, this white is means that portion is highlighted. So this mask is highlighting the zebra part, and over here, this mask is highlighting the background, the grass part, right? And then you have this first layer, what it is indicating is the distribution of the feature at that high dimensional space. So what you can think of something like the patch distribution. When you have an image, you have so many patches. What you are able to understand is how these patches are there. And then when I multiply this mask with the image features with respect to the foreground, you will have the zebra image coming out. And then similarly, when I have this mask multiplied that Hadamard product element wise, right? When I multiply with the grass features, in that case the grass will be synthesized. So then in that case, how do I, so mainly what was the motivating example? The image decomposition. What I wanted to know, what is the mask in the image segmentation problem. Similarly, you can have another problem which is like your image dehazing problem, in which suppose you have an image and lot of noise is there. This is an example with respect to the natural corruption. That natural corruption can also be there in the case of manuscript images, right? So what you have is an image in which because dehazing is one of the difficult example, because there is no physical formula through which you know the distribution of the noise particles, right? That's why people describe it with the image dehazing example. So what you have is you have this corrupted image, and what you want is this haze-free image. So in that case, what you do, you have this corrupted image and figure out that mask. That mask is nothing but showing with respect to T map. So this mask is nothing but a variable when multiplied with some output plus 1 minus of that mask multiplied with the air light. What is this distribution of particles? That is going to compose me this particular image. So what we are going to do, if you remember, I have described one function here. There will be two functions here, one for this part and one for this part. Similarly, one function will be for this part, one function will be there for this part. Similarly, the transparency separation problem is there. So mainly, what is happening here? So in the case of image decomposition problem, you will be able to figure out the segmentation mask. So this particular image was so well, very corrupted, so the mask is not of that good quality. But what I am trying to describe is the mathematical formulation. And what is the mathematical formulation? For an image, it can have two, because it's a decomposition at the level of 2 only. So for an image, what you have, suppose you have hazy image, in that case you have hazy particle and the natural scene. In that case, you will have one network which is going to identify the haze-free image, and the one network which is going to identify the haze particle. And then you will have a mask which is going to, this M is nothing but your mask, which is going to multiply it, and then this is the composition of this. And this composition, you are going to match with respect to your the given input corrupted image. So what we are describing over here is, basically, you had only a corrupted image, you want to decompose it. In that case, you take two networks. One network is going to identify one set of features, second network is going to identify second set of features. You do the composition of them through this, and then do the pixel difference with respect to your input image. And when you will do the pixel difference with respect to input image, these will be the meaningful decomposition. This F1 and F2 will be the meaningful decomposition. And that depends upon what type of application you want to employ. Accordingly, you can employ. Okay, so one of the works which we have used in this for the SimSam and DLI work. Yeah, I feel this will be more interesting to the audience. This is the style transfer work. So if you see, this is the pioneer work from the Gates et al. So what is happening here is, you have this image, this is, we call the content image. The object, its structure, its shape, all of that is nothing but wherever you are taking. So when I see this image, it has its object and its structure coming out from this particular image, right? So this is your content image. Similarly, when I see this image, it's more about color and textures, right? So this is nothing but your style image. And you can actually perform the style transfer, means the transferring the style features from the style image to the content image, and then the output will look like something like this. Why this is useful in the case of manuscript restoration? You can have manuscript which are losing its color and texture properties. So in that case, you have really good restored, you have really good ground truth, because some of the manuscripts, if you have, which are of having good color, you can use the color and the style features, and then you can incorporate them into the ones which are missing the style features or the texture features. So what is the underlying idea why this actually happens? So if you remember, I have described you this F in the form of this this particular. So this is the, let's say, think of the layer by layer. We are decomposing, or we are thinking of the function F. Because and why it is a functional composition? Because output of this function, or this is the let's say F1, output of this goes to the second one, and then output of the second one goes to the third one, and so on. Right? That's why it's a functional composition. What is actually observed in practice is, when you have an image, for an image, it's different features, style features, or the texture related features, or the content features, which are with respect to your object structure and its properties. They are actually captured at the different levels of the feature maps. So when they are captured at the different levels of the feature map, what you can do, I can take the content features from one particular set of image and take the style features from another set of image, combine them, and then put in my objective. This is the fundamental idea with respect to the style transfer application. So this way we are able to see these kind of restoration are happening. This is very famous in art industry. Many people, because many famous painters or many famous artists are no more. And if you want to see any specific art in their form, it's there. So you can utilize their art, their style of making art, and you can incorporate them in any specific design which you want. And CVPR, which is one of the top places, they also organize a lot of workshop regarding the same every year. So this is one example. You can see similarly more examples are there. You have, this is your content image, this is your style image, and these kind of outputs will come. Similarly, this is the second example. Okay. So now, why this is relevant in the case of manuscript restoration? Because you can have manuscript images in which the color or the texture properties are lost. So you can utilize some of the existing ones, and you can incorporate the color and the texture properties in the manuscript images through the style transfer work. And this is actually the mathematical formulation for the style transfer problem. So what is the mathematical framework? So what we are talking about, the content features and the style features in an image, right? So in that case, this is denoting your content image, and this is denoting your style image. And then you have the both two objectives here. One objective with respect to incorporating the content features in your output, and the second objective is with respect to incorporating the style features in your output. And this phi is nothing but that network which is going to extract features at the different hierarchies. Means when you are employing this phi, and I can only focus on the content layers. when I am thinking of the objective with respect to content features, and when I am utilizing with respect to the style features, I can only focus on the feature maps which are relevant for the style features. And accordingly, I can formulate this objective, and then my output will be a merge of the content and style features from the different set of images. Okay. Lastly, one of the important framework is this Gyan framework, and so I think 2 days back when I checked number of citations for the first paper which came on this generative adversarial network, the generative model, it had more, I think more than 79,000 citations. And believe me, when I worked on this particular task, this is so old, 2014 in our computer vision research area is actually very old. If something is more than 2 years, it's old. This is how our research goes. So I don't even used to cite this paper. So that, and even many papers are there. So what I'm saying is this 80,000 citations which are there for this first paper that are not incorporating the citations from the last 4-5 years. So it can be more than 1 lakh easily for sure. How many people have used this idea? So what is the idea over here? So basically the idea is simply, you have two networks. You have a generator network and you have a discriminator network. What is happening? You have some noise. From noise, you are going to feed it to your generator network. It will create a synthetic sample. Generator is nothing but, think of an artist. He is blindfolded. Why he is blindfolded? Because you are not supplying the real samples to the generator. That's why it's blindfolded. You are supplying some noise. It will create a synthetic sample. And then you have a discriminator, which is going to distinguish between the real samples and the synthetic samples. Discriminator does not know which sample is coming, but it is going to distinguish. Or basically what it is going to give you a probability value, or nothing but some value between 0 and 1. If that value is 1, it means it's coming from the real sample, and if that value is close to 0, it means it's a fake sample. And this is a simple framework which we call the generative adversarial network. Why we call it an adversarial network framework? Because you have this G and D are against fighting with each other. G is saying, I want to synthesize a sample which will fool the discriminator, and the discriminator task is to identify the real samples. Means both of them have the different set of objective. G want to synthesize samples which fools the discriminator, and the discriminator network want to identify the fake samples. And when you put up this framework, and so obviously this is unsupervised because over here we are not using any labels, right? And then when you have this framework in place, you will be able to synthesize realistic samples. Means that that thing which I was discussing, that you have people who are who doesn't even exist and faces of those people are there, or maybe AI model is able to synthesize. What exactly is happening at the end? Basically, if you see the image space, I have already described that image space is very huge. We cannot really see that image space or explore that image space. What do? You think of a lower dimensional space, right? So map that image space to the low dimensional space, and then the points from the low dimensional space map back to the image space. So your this low dimensional to higher dimensional mapping is done by this G. Because the low dimensional mapping we can do, because when you are mapping these high dimensional images into the low dimensional, just 2 minutes. So when you are mapping these high dimensional images to the low dimensional, you can actually do some kind of feature engineering. If you have an image in which, let's say, the person does not have glass, you put some values in that and then do the reconstruction, it will have started having glass. This is how this ideology works. So this is just the introduction, and what in the case of restoration, what is important in the case of Gyan inversion, basically you use a pre-trained sample generator, or you use a pre-trained generator network. And then again the same story, you take the output of the network, degrade it and match with the manuscript image, and accordingly the parameters will adjust and you will have the restored image as your output. So this is, but this optimization is on the image, not the parameters. So that is one difference with respect to the earlier objectives. Okay, so when I see in terms of the summary, the manuscript restoration task are nothing but denoising, inpainting, deblurring and super resolution. You can do via image reconstruction framework. For script segmentation, you can actually utilize the image decomposition framework. Style transfer framework you can utilize for the visual enhancement of the features, and the Gyan inversion you can actually utilize for the as a prior for creating very high quality samples. Because when I see these have some limitations. When you want to synthesize very high dimensional, very good quality images, over there you have to go for the generative adversarial networks. Okay, these are some of the snapshots of the papers which I have written. This is the image superposition and denoising problem. This is image enhancement problem. Maybe you can see this is more exciting. You have an image and you say that I want to incorporate features with respect to desert sand. So you are giving a text. What I have described for the image, even you can give some text and accordingly the features will be incorporated, and this is your image inpainting task. So I am also starting a project which is mainly for the manuscript restoration. That is a 3-year project. This is supported by PMECRG grants. Recently I have got the notification, and in that project many specific more details are involved. What I have described is with respect to mainly the image restoration model and the neural style transfer models. There are also a couple of models which have come which are called the vision and language model. Means whatever addition or whatever changes you want in your input image, you can supply that in the form of text, and then accordingly the outputs will be done. So this is your one more detail about the vision and language model. And if anyone is interested in knowing more about this project and further understanding what are my goals in this project, please feel free to contact me. These are the references for my papers. These are the papers for the restoration task, and these are the papers for the image enhancement and the segmentation. Thank you.
Thank you very much. That was a very interesting presentation. So if we want to get a manuscript which is not clear, the image is not clear, are we supposed to go through all these, or we can simply approach you and get it done? Very practical, because I just found one manuscript with me which is not clear.
Yes, you can directly approach me.
Okay.
Because I have students, I'm giving them different data sets.
Yeah.
So what I have given them is the Indic manuscript data set from the University of Pennsylvania.
Okay.
So that I have given, and the images are of good quality there. What I want is the corrupted image. I don't want the...
So I have a corrupted image with me.
So that will be great for me.
Okay, thank you very much. Thank you.
Any questions from students?
My question is for Dr. Indra. What are the similarities between deepfake models and deep internal learning models? And could combining these two can lead to new artistic or creative application for manuscript and image restorations? Thank you.
That's actually an excellent question. So see, when I think of this deepfake model, at the background what we are discussing about the deep generative models. What do we mean by generative models? Basically what I described is like you want to synthesize something, and in theory we call it the generative model. And why we call it deep? Because you are utilizing deep neural network. So the internal learning part is mainly for the single image setting, or when you have only 1 or 2 images. And in the case of internal learning, there are 2 setups. One is you start from the scratch, or you utilize a pre-trained model. So if some model is there which is very good for the deepfakes, means it's synthesizing images which are very similar to realistic human faces. So in that case, that model can be used as a pre-trained model to do the restoration related task. because that is what is the Gyan inversion problem which I have described in the last slide. But see, what I want to mention is, I think up till 2018 and 19, our problem in computer vision community used to be like, we are not able to synthesize images which are going to fool any human being that this is a face of a real person or the face of a fake person. But now our problem is different. Now the models are too good to synthesize very realistic sample, and then the research is going towards how do we identify these synthetic images. So the research question has changed. So this will go on and on, but these deepfake model can be used as a pre-trained model for the restoration related tasks.
मेरा बस क्वेश्चन है, लेकिन थोड़ा सा मेरी एक विषय बता दूं कि जब हम लोग पांडुलिपि को देखते हैं तो उसमें 4 समस्याएं आती हैं। पहला ये कि वहाँ से कोई अक्षर जो है वहाँ से मिट गया है तो उसकी हल्की लाइनिंग हमको दिखाई देती है कभी कभी। एक दूसरा होता है कि स्याही फैल गई है तो अब उस पर एक लेयर अलग से आ गया। और तीसरा एक होता है कि फंगल इन्फेक्शन हो गया उस पर, उससे तो उस पर का तो वो तो स्याही हट जाता है, लेकिन अब उसमें फंगल का भी जो है फफूंदी का भी एक निशान हो जाएगा छाप, और एक आपका जो स्याही मिटा है उसका। और फिर होता क्या कि जब वो आपस में सड़ जाते हैं, कभी चिपक जाएंगे तो उसकी लिपि के जो अक्षर उसमें चले जाएंगे उसके और एक दूसरे में ट्रांसफर हो जाते हैं। तो मेरा ये जानना था कि क्या जो अभी तक आपके पास जो सुविधाएं हैं क्या ये कितने प्रतिशत तक शुद्ध हो सकते हैं, या कोई ऐप हो ऐसा जिससे डायरेक्ट हो जाए पूरा?
Yeah, very great. So see, the problems which I have described so far are mainly the restoration in the case of single image setting. But this problem is much challenging. Because I can understand there can be so many different type of corruption which you are dealing. So for these kind of problems, mostly so some of my students are also working on this. What we are thinking is have a model trained on good set of samples, and that model can actually work as a prior to the restoration of the corrupted samples. So mostly in the vision community, when you have models, they are minimum 5,000 or minimum 5,000 samples are required. So if we are able to figure out, let's say 5,000 decent looking samples, in that case, then it will provide a good prior for all of the different corrupted images. But first because if we are finding it difficult, how we can think of an artificial network to do it? It's not a real intelligence, it's an artificial intelligence. So we have to train that intelligence through some of the existing good samples, and then it will do it. That I believe it's possible.
Thank you, sir.